Our next event is Hsai-Yang Fang Lecture, and the professor will host the event. Professor, please. Okay. First of all, I briefly introduce the Hsai-Yang Fang Lecture. This year's and Professor Fang is passed away. So according to the will of the Professor Fang, we set up this lecture. This lecture is in order to memorialize our pioneers of Professor Hsai-Yang Fang, the International Society of Environmental Geotechnology. It's established in the Hsai-Yang Fang Lecture in 2022. The Hsai-Yang Fang Lecture will be awarded to the one awardee at each international symposium organized by ISEG. And the awardees will deliver the lectures at the symposium. There are procedures. Each the ISEG Council member has the right to nominate one candidate who has made the extraordinary contributions to the environmental geotechnology. After nominations process, all council committees members vote for the one awardee or the nominee. So this year, after the official and council committees votes, Professor Hsai-Yang Fang as the first awardee of the Hsai-Yang Fang Lecture. So it's Hilary I, he is the component and the honorary president of the International Society for Environmental Geotechnology. He is fellow of African Academy of the Science, US and basis speak business foreign for the Symposium. President and chief executive office of the Global Institute of the Sustainable Development, Advanced Analysis and Design, and according to North USA. Professor in the new energies and gold distinguished professor of the environmental engineering science and founding director of the Global Institute for the Energy and Environmental System, University of the North Carolina, Canada, and Professor Vice Chancellor of the African University of the Science and Technology, Abuja, and Nigeria. Okay, welcome to the Hsai-Yang Fang, okay, with the Senate and the Hsai-Yang Fang Lecture. Hello?
Hello. Okay. Professor Shibin, is the floor open to me?
Yeah, I'll hear you.
Okay. Thank you. Thank you. Thank you very, very much. Professor Shibin, President of ISEG, Professor Hsai-Yang Fang, Secretary General of ISEG, the entire Secretariat of ISEG that has done so well for preserving the integrity and the well-being of ISEG. Professor Yumin Chen, the chair of the scientific committee and members of the scientific committee, the vice presidents of ISEG who have been collaborating exceedingly well with the secretariat and the leadership, council members of ISEG, the secretariat itself, distinguished academicians, and other participants. I thank you very much for the opportunity given to me, my humble self, to be the one to deliver the lecture. As you know, H.Y. Fang made seminal contributions to the advancement of the field of environmental geotechnology, all looked up to, and that was befitting to him as the patron of ISEG and the co-founder of ISEG. He was very selfless and worked with many young people and people of his age group and people of diverse ethnicity, that a lot of people were brought into ISEG and given opportunities to rise and shine, as you would say it. It is also befitting that this first ISEG lecture is given through the time that the ISEG is headquartered in Nanjing University, because Nanjing University played a seminal role in the formative stages of ISEG. A lot of things were done there, and of course, the present president and secretary general also come out of there. I can remember 1999 and 1998 when Professor H.Y. Fang and I visited Nanjing University, and the support that the president of Nanjing University gave us at that time. So we are very grateful, and I in particular, extremely grateful for the opportunity to talk today to all through the instrumentality of Nanjing University. I hope that everybody can get on to the slide. The title of my speech today is Physico-Chemical Interactions and Textural Response in Geomaterials. And I chose this topic because it was an area that Professor Fang worked on for more than 50 years. And developments in this area have been seminal to the establishment of the field of geoenvironmental engineering using the broader nomenclature that is used worldwide. So I hope that when folks listen to some of the concepts and some of the experimental and theoretical configurations of my talk today, that we will all remember H.Y. Fang for his many contributions across the field. Let's proceed. I have decided to look at physico-chemical interactions in soils in the surficial environment, which is a dynamic zone. Why? The surficial environment of soil, or in general geomedia, is dynamic because of many gradients. There are many processes that happen there. The weathering of geomaterials introduces many mineralogical phases into soil composition. And there are gradients within phenomena, be it diffusion, be it chemical interactions, be it the speed of reaction, and all of these are underlain by physico-chemical interactions that cause textural changes. So we will look at a few of them today within the context of soil strength and durability development, and also within the context of soil permeability and porosity that are so important in the relatively new field of environmental geotechnology. Next, please. What you are seeing now is just an illustration of the surficial environment in soil and a lot of processes that happen there. You also see that there is a dashed line, some displacement from the ground surface called the root zone. Although this zone is typically removed in geotechnical work, scraped off, because it's often the organically active part of soil, the superficial soil. It is usually scraped off during construction processes on the geomedium. It still exposes the remaining part of the superficial soil to many gradients that we have already mentioned in my last slide. So essentially, the superficial environment in soil is one of many physical, chemical, and biological processes that have implications on soil structure, and then in turn, implications on soil strength and durability, as well as permeability, porosity, and many other parameters that are important to us in environmental geotechnology. Next, please. I need not go through every one of these physical-chemical interactions, but suffice it to say that most of them have been recognized by others. I'm just using the seasonal processes here in the temperate zones of the world. Nanjing is part of the temperate zone of the world. Much of North America is, much of Europe is, but Bullock and his friends and his collaborators as early as 1988 had mapped out a lot of the physical-chemical processes in soil that are responsible for development of soil texture in that zone of the world. We take a look at this. I will not read them all. You see that there is a displacement of soil by ice expansion during certain months of the year, general snow precipitation, freeze-thaw action that affects soil structure and soil texture, and then occasional tillage and compaction disrupt significant portion of existing bonds in soil, diurnal thawing and freezing. Ice also displaces some soil particles in its action, and many other physical-chemical parameters and processes that are not described in this simple illustration. Next, please. And some years ago, Professor Fang actually participated in this work. We had a student at the University of Massachusetts Lowell when I was there. His name was Roddy, and he worked with us on soil desiccation processes and how soil desiccation processes in the near surface zone affects the development of flow channels. Of course, those flow channels compromise the integrity of barriers that may be buried in that soil. So what you see there are desiccation cracks by illustration that develop in a grout, a linear grout configuration that has been put across the soil profile near the ground surface. Obviously, the drying effects that are common to superficial soils, especially when you have temperature gradients, would introduce some flaws that could have implications on the flow of contaminants through that barrier that you see there. And we actually did a mapping through using many new techniques. In some cases, we use pulse echo. In other cases, we use sonic wave velocity. And we established the presence of flaws on what we would call slice porosities. And these slice porosities are shown there. As you see, along with axial distance, it's a variation of slice porosity, showing that there have been some cracks that developed in that soil. So this is an illustration of physical-chemical interactions, although some may like to think that desiccation is just a physical process, it is not. There are some implications and contributions of the clay particles of those grouts and processes that involve diffusion of moisture from down to up or from sidewards to sidewards, which are classic cases of physical-chemical interactions. And they manifest in some cases as the cracks that we have seen in this illustration. Next, please. So let's go further into physical-chemical interactions within the context of two main areas of work in geoenvironmental engineering. The first one is in the area of soil strength and durability. Of course, this is pretty much part of established customary geotechnology. Geotechnical engineering has had this for a very long time. And some of the things that are within it in terms of professional work, soil stabilization and grouting for strength, contaminant encapsulation in soils, irrigation implementation that is also common to the field of agriculture, soil desiccation analysis, which has been a focus of many works in research in many parts of the world, including even Nanjing University, where my very good friend, Professor Hsai-Yang Tang has been working on for years. Slope stability. I know that this is the area of involvement of many of the council members of ISEG, and of course, bearing capacity of soil foundations that many have engaged in for many years, among whom has been Professor Fang, starting from his publication of that book, the seminal book in foundation engineering that is used worldwide by students and researchers. That's the foundation engineering handbook that he published about 40 or so years ago. So we will look at that. We will also look at the implications of soil textural changes that derive from physico-chemical interactions in the area, the newer areas of geoenvironmental engineering and environmental geotechnology. That will be later. But let's look at section B, dealing with physico-chemical interactions within the framework of soil strength development and durability preservation. One of the areas of work in which physico-chemical interactions is very profound is in the area of soil strength improvement. It could be improvement using grouts or pumping slurry in for stabilization. Way back, Malone and all in 1982 had developed a guide for using grouts in soils. You see that organic polymers can be introduced into soil, soil that have textural ranges from fine to up to coarse silt, right? So you see here, organic polymers can be used to grout soil for improvement. Chrome lignin. Lignin is from wood. It's a polymer that comes from wood. And then resins, sometimes silicate cement, sometimes even bentonite clay, sometimes Portland cement. The interaction of all these substances with soil are in the physico-chemical range. And the extent to which those reactions can complete and help in changing the porosity, reduction of porosity, is one of the objectives of grout stabilization of soils. So that shows that we can induce some physico-chemical interaction in soils for beneficial purposes of strength development, strength improvement, and in most cases, durability too, because durability pertains to how long that strength will stay over time. Next, please. Then, of course, there are some guides too. Others have worked on this. You see that there's a classification system for grouts. You can have particulate clouds, you can have chemical grouts as well. Particulate clouds generally interact mostly physically with soil, but the chemical grouts interact with soil in a physico-chemical way. And there are processes such as gelation, coating of mineral grains so that they would attach with other constituents of the soil agglomerate to improve cohesion. And sometimes reactions that help improve the internal friction of soil. There are other manifestations of physico-chemical interactions and composition of the grouts themselves. The stability, which describes the extent to which the particles of the grout remain in suspension. Of course, we want the particles to remain in suspension in the initial time during the pumping of the slurry into soil. And then setting time is also important because it is the time that is required for the grout to harden it is important that the ground doesn't harden too quickly before it gets to locations of placement that are intended in soil. It will typically pump in. Then there is the viscosity of the soil, which is a proportionality parameter that relates the shear resistance of the fluid that is pumped into soil to the velocity gradient. Obviously, we know that if substances are of low viscosity, they tend to flow faster than substances that are more viscous. Of course, in environmental geotechnology, we are no longer dealing, in most cases, with water as the permeant in soil, but we are dealing with substances, fluids that have chemistry that is different from water. So we should expect some sort of chemical reactions, no matter how low in profundity, no matter how long it takes. Those processes go on and are favored by the thermodynamics of the system, although the kinetics may be very slow. Because in soils, we are not dealing with pure substances. We are dealing with multi-mineralogic situations in which you have a texture, particle size, and each particle may be composed of many minerals, so that we don't have the stoichiometry that you would have with chemical engineers and pure chemistry who deal with purer substances in their reactions. Another thing that we tried to do in the past with respect to looking at physical-chemical interactions and the generation of texture in soils was to look at all this work that is being done in the area of use of ashes, be it fly ash and many other types of ashes and slags used to stabilize soil. So what you see here is a schematic drawing of fly ash particles interacting with clay particles in soil. This was popular some years ago. I'm sure that it's still popular in the developing world. The use of fly ash in liners of landfills and other kinds of barriers, because obviously firms in the US that manufacture and some of the flies as class and another class, I've forgotten the designation. And one of the classes is very reactive on the surfaces with other substances that may be put in soil, other components. So what you see here is the fact that some cementitious behavior of fly ash can be helpful on the picture on the right-hand side in interaction with clay particles. And by cutting off the connections among the clay particles and clay clots, it might be possible to reduce the shrink swell potential of that soil mass. So physical-chemical interactions in soils can help in promoting the generation of certain beneficial properties of the soil mass, of the soil mix. This is an example of work that Professor Fleming, who is now retired, who was at Howard University, and myself did in 1995. You see those textures. Sometimes flaws are generated because cementation sometimes involves the generation of tensile cracks in materials. And tensile cracks are one of the parameters that are used to describe texture of the cross-section of a material. And you see that cracks are generated on the right-hand side, the lower part of that diagram, because of those interactions. And on the left-hand side, the initial stages. On the right-hand side are subsequent stages when those reactions have occurred. Usually the reactions would occur on the surfaces of grains first. In some cases, if the reaction energy is still left, you might have the generation of some seams that go inside the particles as the reactions proceed from the surface of the particles to the interior part of the particles. Another work that we did that we are proud of sorts was sponsored by DuPont Corporation at the University of Massachusetts, Lowell. When I was there, I spent 1995 to 2000 there as a DuPont professor with some of the ISEG Council members, like those I can recall, John Daniels and Ogunro, who are now full-fledged professors at the University of North Carolina, Charlotte. But there were many other students who worked with us who have gone on to professional greatness. And I can also say that at that time, we were lucky to have the current president of ISEG, Professor Shibin, join us as a visiting researcher and worked on so many things in the area of soil texture with us. And just one of those things that we did was the stabilization of soil using polymers. Some may ask, why polymers? Because we wanted at that time to improve the integrity of clay barriers so that they would not dry out in the dry season and then expand in the wet season when the water would be readily available. And we experimented with many chemicals. So in this chart, you see that there are many polymers that we experimented with: polyethylene oxide, polyethylene oxide, polyethylene glycol, polyethylene polyvinyl alcohol, which is very well known in many situations, carbametaxyl cellulose, and many other types. These are just examples. Some of them were neutrally charged. Obviously, when they would be neutrally charged, that means that we would not expect a lot of chemical part of interactions with clay soil particles. So it could just be the issue of cohesion that they would help by being somewhat more viscous than water. So they would just act as sort of glue, gluing soil particles together. Obviously, this would be more relevant to the case of granular soils. You know that granular soils are mostly composed of silica, and silica is satisfied. It does not have negative charges in the same way as clayey soils do. So the clayey soils we typically encounter that show this expansive behavior are negatively charged clayey soils. So if we add polymers that are positively charged, we would expect some sort of physical-chemical interaction between the positively charged polymers and the negatively charged clay surfaces. So this was the conceptual rationale for us using some of these polymers that were positively charged. There are some that were negatively charged too, but that process in soil would be that of dispersion. And in some cases, we made use of that process. But these are some of the results that we received. Intrinsic velocity that we got, and the dynamically equivalent sphere. That is, if we take that polymer and the polymer shows a configuration in a liquid, how can we describe that? How would that polymer be able to taxi into the interlayer space of clays? This is very important because in order to stabilize soils in a way that is durable, the polymers had to be of a size of a hydrodynamically equivalent square that can swim into the interlayers of that clay composite. Let's proceed. And we succeeded in doing that. These have implications in the stability of slurry walls. You know that slurry walls have been used in geotechnical engineering for so many years in the area of holding back cells from flowing, in the area of waste containment as well. It came into practice way before environmental geotechnology. This illustration was done by Costello and me in 1988. Go back, go down, go down. You can also see a situation in which physical-chemical interactions between soils and other substances can be used in slurry walls to help hold back soil that is inherently layered and unstable. I derived this equation with the water table that can roam from the ground surface to way down there, using the equal stress method of making sure that the slurry, as you see there in that trench, would have enough resistance to hold back the soil strata from falling into it. Because whenever slurry walls are used as vertical barriers to control migration of moisture, it is important that some of the more granular soils that make up the walls of the trench don't fall into the slurry. If that happens, what typically happens is that you have windows of high porosity and permeability through which the water that you wanted to prevent from migrating can migrate. So how can that be established? How can that be accomplished? And how can that be done? We can put some substances that help improve the density of this slurry, because the mobilization of strength by this slurry will depend on the density. If it still stays as a very low viscosity fluid, it will not be able to counter the effect, the sliding tendencies of the walls of this trench. So physico-chemical interactions are very important in the sense that if in this slurry, we have the development of texture that can offer more resistance to the sliding, then we have succeeded. So this is another illustration of the manifestation of physico-chemical interactions in a physical way to help improve the resistance of geomaterials when we have these kinds of applications. Next, please. We have many ways by which we can improve these geomaterials through the use of additives. And this has become a very important area of environmental geotechnology, being that it derived even from earlier work in environment, in geotechnology itself, soil stabilization. Soil stabilization has been in practice for so many years, starting from when foundations had to be improved in many parts of the world, when subgrades for roadways had to be improved so that the roadway would be stable for many years under traffic. But things have moved on from there to the use of these additive materials to generate low porosity and low permeability in soils in the practices in the field of environmental geotechnology. And our departed colleague, Professor Hsai-Yang Fang, was very active in this area. We have used granulated slags in geoenvironmental engineering and high lime ashes in cement-based mixes to reduce permeability. We have used innovative materials such as phosphate bonded ash cement, which has a very high compressive strength and low porosity in many areas of waste containment, including the containment of radioactive waste, because that increase in density is very important. As you know, the transport of radiation in geomaterials is indirectly proportional to the density of the layer through which those rays travel, gamma rays. So if we can improve the density of geomaterials, we can use them as barriers in temporary containment of radioactive waste. And this is being done in the United States, Europe, and even Asia, and may also find application with more research in deep-seated disposal of high-level radioactive waste for miles in the ground. Secondly, the addition of iron oxides to cement, okay? And other materials such as hematite. Iron oxide comes in many forms. You can have hematite, which is Fe2O3. You can have magnetite, which is Fe3O4. And sometimes you can also have some iron filings that are being used these days in permeable barriers. So these substances make use of certain physico-chemical interactions that may have manifestations in texture and then manifestations in strength and durability, and manifestations in many other kinds of desirable characteristics, such as barrier to the migration of contaminants and barrier to the migration of radiation through layers. There are others that are very well known: activated carbon, a topol gate. A topol gate is a form of clay, topolgite should be, organoclays, resins, and other biomaterials. And one of the areas that Professor Fang worked on, even before my time in environmental geotechnology, was in the area of application of certain types of mixes of soils in slurry walls. And of course, at that time, people like Da Apollonia was a practicing engineer in the United States, very prominent in activities of the ASCE, American Society of Civil Engineers. As early as 1982, had published a guide for the use of soil mixes in slurry walls, and it had established that the minus 200 sieve, that's clayey soils, the content of that had great impact on the permeability of slurry wall backfills. As you see there, not only is the content important, but the mineralogy. You see that on the diagram on the left, you have non-plastic and low plasticity fines. So you have the non-plastic ones that exhibit higher permeability than the plastic ones. The plastic ones have lower permeability because they are typically made up of sodium morphorilonite, which is more plastic than calcium morphorilonite and other fines that are of very low plasticity. So in physical-chemical interactions in soils, particle size is important, as well as mineralogy of the soil particles themselves. This is what this illustrates. Let's go to the next slide. And sometimes we have cement put in soils to promote certain types of characteristics. One of the important types of reactions in soils is cement-clay reactions. Sometimes you can even have this as an attack of structures that are buried. Sulfate attack is a very well-known one that can cause textural changes in soils and other components that may not be natural soil, but components of structures in soil. For example, a landfill layer or a cemented barrier that is buried in soil. That equation is shown there. You have 3 moles of calcium oxide, one that has aluminum oxide, alumina, as we call it, attached to it. In the presence of water and calcium sulfate, will generate calcium oxide and alumina calcium sulfate and some moles, 12 moles of water. Then you can have the monosulfate then combine with calcium sulfate and water to produce other things. One of the most important products of these reactions is a substance called ettringite. Ettringite has a texture that may be of significance with respect to soil strength. The ettringite itself can fill pore spaces in soil. It can also expand the structure of the barrier material such that we have the generation of cracks. So these kinds of interactions that can be assessed with partial stoichiometry. I say partial because often you have too many substances that are there for stoichiometric analysis to work. And stoichiometry works much more when you are dealing with pure substances like the chemists deal with, and chemical engineers deal with. But in soil, it is more complicated. So we have to use some modifications, but we know that at the fundamental level, those processes contribute. So we need to understand them, although the manifestation in the meso scale and macro scale may not follow what it normally would if we had pure reactions. We don't have pure reactions because of the composition of soil. It is very, very, very macro. It has many, many constituent minerals that are difficult to even describe because of substitution of cations and many, many changing phases under different temperatures and EH conditions. One of the areas, you see that the person who did this work, move that barrier off so you can see. This was one of Fang's work, and we used to sit down, myself and him and others, to look at this model. Because at that time, we were trying to establish the life cycle of some structures. I dealt mostly with waste containment systems, but he was more interested in a broader sense of geostructures in soil. Of course, we had established a model that was somewhat similar to this, but with many other factors included in my own. But this was the original thing that he did himself in 1984. That if you want to track crack development in geomaterials during the service life of a structure, it is possible to draw a configuration of this sort, that the growth of cracks in the vertical axis versus cycles of stress. Obviously, cycles of stress also could be taken as the evolution of time, because cycles of stress take time. So he identified three main zones in that curve of the growth of cracks with time. There's the initial time in which the structure is still of high integrity, so that you don't expect a lot of cracking. That is why you have a very low slope for that initial stage, that C sub I stage. And then you go to a stage that we often call in general engineering mechanics as a stage of runaway cracks, that you have the cracks that now begin to extend. In engineering mechanics, they usually use the term flaws. The flaws begin to expand over time. This is an area in which the flaws have already existed so that they do not need so much energy to grow in size and of certain shapes. Of course, the growth in size will also depend on the resistance of the structure, whether it is highly cemented or weakly cemented, all of which can be manifested in the tensile strength of the material. We like to see failure in materials as being induced by tensile stresses, that is the splitting apart. This is why we are so concerned with brittle materials, materials that have low tensile strength relative to their compressive strength. But then you have that final stage in which the cracks have gone so high that we can even say that the material has failed. So any attempt to strengthen the material for the long term, in other words, to make, one has to try to do something by understanding the dynamics of crack development or other kinds of failures. This was Fang's work. Of course, we had extended our own in the estimation of the reliability of waste containment systems over very long periods of time, in which small cracks that are initial could have a lot of implications on fluid flow in the long term. Because in that regard, we are thinking of more than 1,000 years of service as specified by laws in the United States. I know that China is now very active also in deep disposal of radioactive waste. And this will become as important in China as it has been in the United States. In that case, I and my associates and my students and my postdocs and so forth had to adopt more elaborate descriptions for this type of failure, taking into consideration that there might be some events that happen abruptly, like earthquake, like sliding, even down there in the deep geostratum. We can have that. So our curves are not this smooth. But this seminal work was very helpful in establishing many of those models that came later. So this is also a tribute to Professor Hsai-Yang Fang. Now, he further, of course, dealt with the issues of the processes of wetting and drying in soils and how those set up drying and shrinkages and stresses that are relieved by desiccation. And desiccation generally means the proliferation of cracks in a material. We've already talked about this earlier on, but the superficial environment is that of many gradients, including gradients in relative humidity, in which case sometimes the relative humidity above the soil layer is low, so that you have a lot of evaporation, and evaporation generates stresses in materials. So the surfaces of soils tend to crack. Sometimes they have a certain well-defined pattern. I think all of us are familiar with hexagonal cracks in mud that is exposed over a long period of time in many parts of the world. This phenomena that Frank also described, along with many others. This is not a new field, and it wasn't a new field in 1994 because it had been there in agriculture for a very long time, for many, many, many decades. People in soil science were working on this, but we tried to bring this aspect into geoenvironmental engineering as early as the 1990s, and this is just an example of what Frank did himself in this context. Then there are other people like Heyman and Ellsborough and Speak, as early as 1988 and 1987, were showing illustrations of what would happen in barriers. Those were the times where work on barrier, where in waste containment systems were very profound. And it coincided with developments in many parts of the world. India was also active in this. Of course, you know, one of the people was also working in these physico-chemical interactions at the time. He's one of the vice presidents of ISEG, Professor Hsai-Yang, my collaborator and friend at the Indian Institute of Technology. So a lot of people contributed to advancement of waste containment barrier systems. People like David Daniels and many others were working on this, and my collaborators at Kansas State University, who helped me in collaborating with me to offer that textbook, Principles of Geoenvironmental Engineering in the 1990s, were also active here. Many people at the University of Chicago, Illinois, one of whom is Vice President of ISEG today, our friend at University of Chicago, Illinois, and many others worldwide were active in this area of work. But what is important here is that these physical-chemical interactions may influence the micropermeability of soils and eventually the macropermeability of soils, as you see on the right-hand side. When we get to the sector of this lecture that deals with environmental geotechnology, we will look at this again in greater detail as to how this happens. Of course, for some of us, we have been interested in, because it is not just important that cracks develop in soil, but the orientation of the crack. The soil is not transparent. So how do we then establish the orientation of the cracks and the connectivity of the cracks? This branch of study, of course, we all know is called stereology. Stereology tries to establish the connection among flaws in a material that may not necessarily be transparent. It would be transparent if you are considering glass, and there is a fair amount of theoretical research in glass materials that are transparent, but in soil it is not. So we have to use indirect methods, either by modeling to sense the connectivity of those cracks. Scott as early as 1988, and also the work of Professor Shibin cannot be ignored in this area, because when he joined us at the University of Massachusetts Lowell, we and later on at University of North Carolina, Charlotte, my collaboration with him was mostly in this area. How can we use GIS to describe the surface outlay of floors? How can we use serology to look at deep penetration of floors? Why is deep penetration important to us? It is because the existence of floors themselves may not contribute so much to the migration of substances in geomaterials unless the cracks are interconnected. And the interconnectedness of floors determine the permeability of the layer of concern, not just the porosity, but the interconnectedness of the fractures and other kinds of flaws, pores in the material. And we tried to, as you see on the left-hand side, I did not publish that work. It's yet to be published. It's just among many other things that we did at the time. You see the illustration there, but on the right-hand side is the proper illustration of the significance of the interconnectedness of cracks in a geomedium. And those cracks may be generated as a result of physicochemical interactions and responses to stress gradients in the near surface, where we are typically active as geoenvironmental engineers, because we don't deal much with 1 mile in the ground. It is only recently that folks are concerned about that when you talk about carbon sequestration. Because we are talking about deep down there. We also talk about radioactive waste disposal. That is high-level radioactive waste disposal, in which we are concerned with depths that may be up to 1 kilometer down there. Let's deal. And it is fair to say.
There is 10 minutes left. 10 minutes left.
Okay, I have 10 minutes left. Let me. Okay, so in the next 10 minutes, I'll try to conclude. Let's say that. Let me also show this aspect of Fang's work. Of course, we know from traditional geoenvironmental engineering that clay particles can be flocculated or could be dispersed. And whether that is dispersed or flocculated has many textural implications. And that texture also affects many parameters of soil strength and permeability. Fang very earlier on worked on illustration of what at that time was how we saw the disposition of clays when once they come into contact with certain types of chemicals, which I have chosen to call physico-chemical interactions in this lecture. So that's the illustration he showed, that initially you can have clays that are like what you see on the left-hand side, and then the clays can get flocculated. Typically, flocculation of clays is caused by a decrease in the thickness of the double layer. Flocculated clays have a reduction in the thickness of the double layer. And the reduction in the thickness of the double layer can cause reorientation of particles. Usually, the flocculation is because of a haphazard attraction. That's what you see in section A. What you see in A is haphazard interaction. You would think that reduction in the double layer would actually bring the particles together so that you would have reduced porosity. No, because the attraction of edges to the flat portions of the clay platelets are somewhat scattered. And as a result, you have an enclosure of larger pores than you would have had in a dispersed state that you see there at the bottom, the more dispersed state. That is the dispersed state, but the flocculated state generally allows more porosity and not necessarily increase in porosity in certain directions. Because previously the clay was more aligned. So you would have porosity or permeability anisotropy, in which flow in one direction is more than flow in the other direction. As you would see in the displaced structure, obviously, vertical permeability would be much less than horizontal permeability in this case, in the displaced state. That's another area of work that physical-chemical interactions are very important, is soil desiccation. I've talked about soil desiccation within the context of agriculture, but there's also soil desiccation within the context of human health. In many parts of the world, the roadways are not tarred. As a matter of fact, I took this picture in Brazil when I went there to do, this is my car there that I rented. That was about 2001 when I went there to do research on lateritic soils. Lateritic soils are iron-rich soils. We were interested in dusting because the end result of excessive soil desiccation is dusting. You see that dust is generated there because of the action of that vehicle. Dust may also be generated without the action of vehicles, as it is in many dry parts of the world. But one of the disadvantages of this is that it can soil the ecology of the environment, as you see there. The dust settles on vegetation. Also, people can breathe in this, and this is a big problem that is confronting us at the United Nations right now. I'm very involved in research in this area to keep down dust. And physical-chemical interactions that can be used to help this is soil stabilization with polymers. So because of this, we tried to generate this illustration, which shows the processes of soil desiccation that result in dust generation. Let's see the very first one quickly. Typically, go back. That diagram, please. Yes. You have a situation on the left-hand side where you have liquid evaporation, and then the notches of soil start to appear as the surface of the soil loses moisture. This is my own conceptualization of dust generation from soils as a result of desiccation. And so eventually you have crack density being so high that individual particles may be released. And because they are released, they are no longer heavy. Wind action can easily make them airborne. So that's what you see in the last portion, the one to the right, the diagram that you see to the right. Okay, now, what can we do? We can spread polymers on the soil, but these polymers have to have a certain chemistry that can promote the interaction or cohesion of soil against desiccation stresses. So this is why we prefer polymers, because polymers can act through two mechanisms. One is the chemical bonding of the soil. That is, if these polymers are of positive charges, they can interact with the negative charges of clay, or the fact that these polymers can also act as glue, physical glue, can promote cohesion among soil particles, because the polymer fluid has higher viscosity than water. Water can easily be lost when spread on construction sites because water is of low viscosity and can evaporate much more easily than a polymer, aqueous polymer fluid. Let's go down. And this was part of the work that one of the council members of ISEG, Tony Yongbe, who's now a professor at the university in Korea, who was my PhD student at the time, worked very hard with me on. And there are many others who worked with me on this and have gone to a prominence in. So what you see here is an attempt to see the texture of those clayey soils when we magnify them. What you see on the left is starch. We fabricated, processed this starch from cassava. Cassava is a type of food crop, a tuber that is very common in India, much of West Africa, and some parts of South America. We generated that starch and use it to stabilize clayey soils. And what you see on the right-hand side is the scanning electron microscope studies of this. And how do we relate to this? As I said earlier on, it is
1 minute left.
we have 4 minutes left. Yes, there's no. Okay, so we'll try to end here with 2 minutes. So what you see here is the starch that has taxied into the interlayer of clay on the right-hand side. You see, that's what we hope happens. And we have proven this experimentally. And what I wanted to use this lecture, Hsai-Yang Fang Lecture, to illustrate is that physicochemical interactions in soils affect the texture of soils, and in turn affects the capacity of soil to do well in many environmental geotechnology applications. And this is an area of work in which Hsai-Yang Fang was very active throughout his 50-year career. So with respect to conclusions, we'll now run to conclusions. There are many other areas, as you can see, but some other day in the future, we will deal with that. But in conclusion, let us state that there are still so many areas of work that need to be done in this area. It is important that as ISEG continues in its growth, it becomes the catalyst for a lot of work in this area, in the areas of monitoring, developing new equipment that can non-destructively assess or appraise these physical-chemical interactions that may be responsible for the failure of structures that are constructed with soil. If that is the case, it means that we don't have to deal with waiting till the very end when the structures have already when the structures have already failed. Another thing to note in conclusion is that environmental geotechnology has gone into many other areas, and it needs to. In risk assessment, risk management, this is where we typically are. And in such areas as monitoring in the subsurface, as you see those monitors in red, go on there. And in all of this, in the spirit of what Hsai-Yang Fang used to do, we used to think of environmental geotechnology as a field in which chemistry has come in which physics has come in, which a lot of mathematics has come in which even things like GIS, for example, GIS can be used to describe what you now see by giving coordinates and all that to show the textural changes in materials, and that has been done, as you see here from our work a few years ago. And I will end here by saying that the fact that ISEG has now expanded and brought in people from outlying fields, in the social sciences, in environmental management, in computing sciences, in the biological and ecological sciences, is a very good thing. So I end here with thanks to all of you for listening to me through this time. And I appreciate you are selecting me to give the memorial lecture, the first memorial lecture of my friend, the departed Hsai-Yang Fang, who made so many seminal contributions to the field of environmental geotechnology. And I applaud the effort of all of the folks who will give keynote speeches at this conference. And I thank the Secretariat and Nanjing University and the leadership of ISEG, including all the council members and vice presidents, for giving me this opportunity to talk. I thank you all.
Okay.